Alright guys, in this video, really I just want to kind of review all the main aspects of orbital diagrams. And so, first of all, orbital diagrams, they tend to give a lot more information about the electrons, about the atoms than just the regular electron configuration notation. So like first off, you could actually see the direction of the arrows. Alright, so if you simply write out, for example, 3p5, for electron configuration, that's all you really know. But if you write it out in the electron configuration, you can actually see the direction of the arrows. You can actually see more clearly what's paired and what's unpaired. And those things have actually there are certain properties that comes about having unpaired electrons. So there are certain properties that comes about having paired electrons. And so this is the reason why orbital diagrams are very important. Okay, so let's just kind of talk about quickly some of the aspects of what we have here. So in this orbital diagram that I'm showing you, it's listed in increasing energy. So you can see which orbital diagrams have which sublevel or which energy level has more energy than the other. And so hopefully you remember that the sublevels or energy levels that's closest to the nucleus have the lowest energy, and as the further out you go, the more energy those electrons contain. So obviously energy level number 1, S sublevel, it's much closer to the nucleus, so it has the lowest energy potential of all the other energy levels, sublevels. And then you can see it go in increasing order. So first you have 1s, then it's 2s, after 2s is 2p, after 2p you got 3s, then 3p, then 4s, slightly more energy, 3d, then 4p, 5s, 4d, 5p, then you have 6s, slightly more energy, 4f, 5d, 6p. And so hopefully you can see this in the periodic table. This actually goes in exact order what you'll find on the periodic table. Okay. All right. So a couple of things you have to remember, a couple of important rules, I would say, that you have to remember when writing orbital diagrams. Okay, so the first one is Aufbau's principle, and so basically Aufbau's principle, it just states that electrons try to occupy the lowest energy level as possible. All right, so if you throw in your very first electron, it's going to fit here in the 1s. All right, so you draw your arrow, your 1s, and then you're set, and then basically it kind of fills its way up from there. So never that you will have maybe one electron in 1s and the second electron will go into the 2p unless it was at its excited state. All right, but unless the electrons are excited, if it's in the ground state, this electron here will be in the 1s, and this will be the case until the energy level sublevel is full, and afterwards then it just moves up to the very next energy level. So if I were to add, so I'm gonna quickly just erase this here, and so if I were to add another electron, I'm gonna try to use another electron, it's gonna show up in the 2s. You add your fourth electron, and then it's going to show up the 2s just the opposite direction. And we'll talk about that rule a little bit later. And then more, then you're going to have the 2p, and so on and so forth. So that's Aufbau's principle. So electrons always go in order from the least amount of energy to the greatest amount of energy. The next thing, rule that we have to consider is Pauli exclusion rule. So Pauli exclusion rule just basically tells you that for electrons, only 2 electrons could fit within the orbital, and if they do fit in the orbital, they must have opposite spins. All right, so you have electron spinning this way, so the directions, usually the notation that we tend to use in chemistry, are up and down. So here we say this has a clockwise rotation, and this electron has a counterclockwise. And then when you really kind of think about this, it only makes sense. So electrons then themselves are negatively charged. So if you have a negatively charged particle here, and it's spinning at a particular way. So here we have this electron is basically spinning in this fashion. All right. Now we know that if you put another negative particle next to it, these two are going to naturally repel each other. So how do you go about putting two of the same charged particles in close vicinity of one another? Well, you have them spinning opposite directions. By doing this, they will create different poles. So one north, one south, per se, and that way they could stay much closer together. All right, so that's kind of the point of that. So that's Pauli exclusion principle. So this is the reason why per orbital you could have the maximum number of 2. Now the last rule that we have to think about is Hund's rule. And so what basically Hund's rule is basically stating is that if you have several orbitals within the same sublevel, electrons prefer to be in their own orbital. Unless there are more electrons, then they will double up. So for example, all right, so let's say we have our electrons here. Now we're going to the 2p, okay? You add an electron, the first electron is going to go here. Once you add in your second electron, it will not double up here, all right? This actually takes some energy for this to take place. So instead of doubling up here with the first electron, this second electron, oh, need my eraser, I'm sorry. The second electron will actually prefer to be in its own orbital. Okay, and if you add the third electron, it will do the same. It would rather be in its own orbital. It's only when all the sublevels have an electron in there and you add more electrons, then they will begin to double up. So if you add a fourth electron, it will double up here. A fifth electron, it will double up here. Then a sixth electron, it will double up here. All right, and then once the sublevel is completely filled with electrons, then you can move on to the next energy level sublevel. All right, so that is Hund's rule. All right, so just to show you a couple of examples on how to write orbital diagrams. All right, so let's just say that I want to draw the orbital diagram for the electrons of nitrogen. Okay, so we have nitrogen here, and so we see that nitrogen has 7 electrons. Okay, so you just fill them up accordingly. The first one is going to go down here. So here's your first electron, your second electron, move up to the next energy level, your third electron, your fourth electron, then you have your fifth. So remember, they prefer not to be paired. 6, then lastly, your 7th. So here is the orbital diagram for nitrogen. Okay. Let's look at another example. Let's say we have let's do chlorine. I like chlorine. So chlorine, we look at the periodic table, we see chlorine has 17 electrons. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Whoops. I didn't even follow Hund's rule, so that's my fault there. So let me backtrack. Apologize. So we have 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17. All right, so here is the orbital diagram for chlorine. And we could do the same thing for ions. All right, so for ions, you just got to keep in mind how many electrons we have. There's nothing really crazy about it. It's just that they're just ions. So for example, let's just say that we're looking at a sodium ion. Okay, well, sodium atom has 11 electrons, so the ion here is a +1, so here we have 10 electrons. So I just got to make sure I count 10 electrons for the sodium ion configuration. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here, this is the orbital diagram for a sodium ion. Okay, So that's basically how you draw orbital diagrams for various elements.